In this video, I complete the clock module by creating the inverted clock signal. I buffer and isolate the LEDs so that they are not directly on the clock signals. And I relocate the Power Supervisor to the clock module. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. For the moment, I'm planning on using 74LS series integrated circuits on my breadboards. I haven't quite made up my mind which series I'm going to go for when I actually do the solder up, whether it's going to be the 74HC high-speed CMOS or 74AHC advanced high-speed CMOS. I believe I'm going to be probably leaning towards the advanced high-speed CMOS or AHC, and I guarantee you I'm going to get those letters wrong at some point. But for the breadboard work, I am going to stick with the 74LS series for now. When we get into the conversation about buffering the output to the LEDs so that they are not directly driven from the clock signal or any other signal, there are line drivers that we'll end up using for the bus signals and register signals. But when we've got a small number of LEDs, such as with this clock, we've got a few options that are available to us that make some sense. One of them is the 74LS125 integrated circuit. It is a buffer. It is a quad, so it's got 4 of them on it, 3-state buffer. So I could drive up to 4 LEDs with this. And as I look at this, the propagation delay, if I'm going to be looking for a higher speed clock, upwards of 10 megahertz, or I'm hoping to be even better than that, then the propagation delay on any given IC is going to be important to consider. But not only that, the depth of propagation delay that has to happen for me to go from getting the signal to do something to any particular set of chips to the resulting output on the other side of all of the integrated circuits also has to be considered. The depth of the circuits add up. You can't get a result out of circuit 2 in line until you get a result out of circuit 1. So looking at the quad state buffer, my worst case propagation delay is 22 nanoseconds. That's the LS series. If I look at the HC series, high-speed CMOS series, this isn't TTL compatible now. The guaranteed limit, worst case, of my propagation delay from high to low and low to high are both guaranteed 18 nanoseconds max. But if I look at the AHC, advanced high-speed CMOS, now again, this is for 5 volts. The worst case propagation delay I'm looking at here is 9.5 nanoseconds. That's a pretty good improvement there. But there's more than one way to buffer output. And if you look at an AND gate, I have one here. An AND gate, if you tie the 2 inputs together, then if the inputs are 0, the output is 0. If the inputs are 1 or logic high, the output is 1 logic high. Same thing with an OR gate. Again, if you tie the 2 inputs together, 0 or low is still a low output. Or high high is still a high output. So the question then becomes, can we get any better than 9.5. Oh, actually, I'm going to go back to the TTL, the LS74LS series. Can I get any better than 22 nanoseconds using an AND gate or an OR gate? So if I bring up the AND gate, and I'm going to go look at those propagation delays, propagation time from low to high is 18 nanoseconds. High to low is 18 nanoseconds. That's better than 22. Now that is an quad input AND gate. The quad input OR gate, looking at those, the propagation time from low to high is 15 nanoseconds, worst case. High to low, 15 nanoseconds, worst case. Again, that's better than the line driver, or I'm sorry, the buffer, and it's better than the AND gate. So 4 or 7 nanoseconds doesn't seem like much. But if we have to stack up 2 or 3 or 4 integrated circuits deep from when we ask for a module to do something and the output is produced, those timings are going to end up being significant. Now, that said, right now I'm looking at ways and methods to improve my memory access and even ROM access. And my benchmark right now is 150 nanoseconds. So talking about 4 or 7 nanoseconds seems to be ridiculously tiny in the context of 150 nanoseconds. That said, I still want to make sure that I pay attention to it and make good choices, make good design decisions that will improve my chances of being able to get a higher clock rate. Similar to the buffer conversation, we've got at least three choices, but 3 I'm going to consider on how to invert the clock signal. The most obvious would be an inverter, a 74LS04 inverter, and that's actually what I started with and what I ended up cooking accidentally if you go back and look at the prior videos. The 74LS04 has a propagation time, I'll pull it up here, of 15 nanoseconds. But I'm wondering if we can do better. The 74LS02 is a NOR gate, and again, if you tie the 2 inputs together of a NOR gate, 0 NOR 0 is 1, 1 NOR 1 is 0. That's an inverter. And so if I look at the propagation times for the 74LS02 NOR gate, my worst case is 18 nanoseconds. That actually is not any better. The 74LS00 is a NAND gate. It's a quad input NAND gate, and 0 NAND 0 is 1, and 1 NAND 1 is 0, meaning it also does an inverter function if you tie the 2 inputs together. The propagation delay time on that is 15 nanoseconds, the same as the inverter. Now, I only need 1 inverter, but this has 4 NAND gates on it. I also will end up needing, I believe, at some point down the road, some state where I'm hanging on to a bit of information where I need to construct a set reset latch. And I can construct a set reset latch out of a NAND gate or a NOR gate by using 2 gates that are cross-connected back and forth to each other. Since the NAND gate has a better propagation time and is no worse than that of the inverter, I will be able to use more of this functionality, 3/4 of this chip versus 1/6 of the inverter. I'm going to go ahead and make use of the 74LS00. Okay, the other thing I want to do is I want to take this Power Supervisor, and I want to move that onto the clock board as well, since that's going to be the first thing that receives power on a regular basis. I want to make sure that I'm monitoring that from the get-go. Everything off to the right here is related to the test harness that I put together. So this can go away. And then these two lines over here just carry power and ground from one rail to the other. That leaves this bit here, not including the LED and the resistor, that need to find a new home on the clock board. There's only 3 pins really required for this. It's only 3 pins wide. And I'm going to use one of the LEDs on the clock board in that bar graph to indicate when there's a problem. And then I'm also going to use this resistor, so that'll carry over. Okay, so now to get this wired up. In the last video, I alluded to the fact that I was taking the output signal to the LED, and then from the LED back to the switch, and I could have just as easily taken the output from the timer IC directly to the switch. So as I bring in the 74LS00 that I want to use as the inverter, and the 74LS125, which I'm going to use as the buffer, what it gives me is the sequence of how I want things to flow across. The LED should probably be sitting over here. So if I have the timer circuit being generated here, inverted, and then buffered, and then output, that is a more logical flow to me. And since I want this to be as much a demonstration as it is functional for me, I want that to be at least linear going across. So that means I'm going to have to move this LED over and wire up the NAND gate and the buffer in its place. So let me get the LED moved over and reroute these signals into the right place here. So the LED gets pulled, and then this signal here and this wire here goes to the left hand side of the switch. I'm going to grab a couple of wires here to help me wire this up. So if I then take this and connect it here, I've not changed any functionality except for having removed the LED. Similarly, this line here, which is here, and this line here, which goes to the other side of that switch. Let's see if I can pull this out without making a mess. Well, that goes nowhere as it is anyway. All right, so the other side of the switch is here. And then, so my combined, and I actually put these labels on in such a way, because it does partially cover this cutout, indicating where pin 1 is. I put the labels on deliberately right side up, so that I know which way the pin 1 is. And then I'm going to put the buffer there. So now I've got to move my power and ground over. So power and ground. Well, actually ground and power. Let's call them correct, Adam. And then reaching over here, I've got a couple more wires pre-cut. Here is power. And ground. forgot which way this went. So I believe it's this way. Let me just get power and make sure that I have this wired up properly. Yes, I do. Okay. So now my clock signal can come from here to one input of the inverter, and then I'm going to tie it to the two inputs together. And this output here is the inverted clock. Now, for the buffer, I'm going to use this one for the inverted clock. So this is going to be in pins 1, 2, and 3. I have to tie C1 low, meaning the control line low. That means it's always outputting. And then the output of that buffer can go to the LED. And I'm going to select, use my pen as a pointing device here. I'm going to select this LED here as the clock, and the one right next to it as the inverted clock. Okay, so that's going to go up there. Again, a 220 ohm resistor. And I'm checking to make sure I'm dropping that in correctly and oriented the right way. Some people have OCD about that, and I can too. The other one is the actual non-inverted clock. So I can tie it with either of these two, or I could even tie it all the way back to here. But either of these two lines here are where the two lines of the NAND gate are tied together. Those are the same node, so I can pull that all the way over here and put it right next, such that you can't think and do it at the same time, such that these two LEDs here are clock and inverted clock on that side. Now, I need to tie the output of my automated clock into a buffer. I'm going to use 10, 9, and 8. So 8 is the output, 9 is the input, and 10 needs to be tied low so that it's always outputting. And then so I can take the automated clock and I will tie this to this third LED. As I reach back for another 220 ohm resistor. I've got these things full of resistors. Okay, so 220 ohm resistor. And that happens to fall right in between. So I've got to stretch it just a little bit. Okay, that's accurate. And then I actually think I want to switch where this is wired up. Because if I have this slid to the right, it is the right signal then. So if I trace this line, the right is what's connected and output on the actual clock. So having this the right LED makes more sense to me. And then the output of the manual clock, I can get a little bit longer wire here. The output of the manual clock can go again through the buffer. So these are going to be pins 13, 12, and 11. And pin 11 is my input. Pin 13 again gets tied low. And then the output is presented on pin 11. And that's going to go into this other one that I just wired up. Okay. So that said, I should be able to do this. And okay. What you get is you get this LED that turns on at the same time this LED is turned on. And then this LED is turned on when this LED is turned off. If I switch it over to the manual, my inverted clock is always high until I push this button, and then it comes high, and then it goes back to the inverted clock. And so that is working exactly the way that I intended to. Now, I do have every intention of using CMOS ICs for this, and TTL and CMOS behave differently, and so I really do need to take that into account. CMOS requires that all of the unused inputs get tied either high or low. Don't leave them floating, so that it doesn't change or hurt the behavior of the IC. So in this case, I am not using pins 4, 5, and 6 of the buffer. So pin 4 is going to be tied high, indicating that it's not used. And pin 5 is going to be tied low. Pin 6 is output, so it doesn't need to be connected. Similarly, on the NAND gate, for now, I'm just going to make sure that I'm doing things complete. I'm going to tie each of the inputs low, even though I will come back later and do some cleanup on that. Or, sorry, not cleanup on that. I will come back later and reuse them for something else, more than likely. So, again, I'm just tying these low. I'm leaving the outputs alone so that they are simply unconnected. It's the inputs I'm tying low. Okay. Now, what I was saying about the difference between CMOS and TTL, TTL have pull-up resistors on the input, so if they are left floating, they will gradually or naturally migrate to a high position or logic 1. CMOS do not have the benefit of that, and so as a result, you have to explicitly tie them either high or low, depending on what you want. That seems like a better answer to me anyway, because there are several that have looked at TTL as dragging things high automatically for them, and that feels very non-deterministic to me. I would rather have absolute control over what my inputs are so that I have absolute control over what my outputs are. And so that's how I'm going to approach this build. Everything's going to get wired up whether I use it or not. Okay, so lots of wires, lots of required cleanup. And let me get this out of the way because I will end up scavenging from that and straightening them out and using them. But I will work now on getting this breadboard cleaned up. I realize I haven't actually properly introduced myself in video. I had created a video where I did do that introduction, and, well, it was terrible. Let's just be honest. I had everything scripted out, and with everything scripted out, I sounded like I was reading a script. And I am far better just talking and rambling on than I am actually sounding. What's the word I'm looking for? Sounding like I'm speaking naturally when I'm actually reading. It just doesn't work out. So, who is this fool that can't bother to put together a complete sentence? Well, I am an ERP programmer. I work in IT during the day. I do programming and system administration for an Oracle enterprise resource planning system. And I have been programming for a good part of my career. I do business solutions, so that includes a lot of SQL database type access, and most of my work is dealing with storing or querying over data. But I have always had a passion for electronics. I was going to school originally to be an electronics engineer, and while it was fun and interesting, I really actually found a passion for programming, and that came very easy for me. So that's what I built my career over. I'm lucky to have never really worked a day in my life. Programming, that is. So, recently I found Ben Eater's series on his 8-bit computer, and I was instantly hooked from that. I bought his kits, I assembled his kits, and loved it. I made an attempt to extend his build to 16 bits and had some success and some not success. There are some problems that need to be sorted still. I do have that 16-bit build sitting here, and I'm trying not to scavenge from it, but I may end up doing that. But I've learned a lot along the way, and I have some flaws that I think I can sort out here in a new build. I also found James Sharman's 8-bit computer series where he builds a pipeline CPU. And that seems far more interesting to me than a stepped CPU. So I'm going to make an attempt to build this as a pipelined 16-bit CPU. Now, the 8-bit version has an 8-bit instruction where I'm looking at a 16-bit instruction. 8-bit instruction is 256 different variants of instructions. I'm looking at 65,535 different variants of instruction, and that's a lot of instructions. So I've got some ideas on how I'm going to whittle that down and make it a little bit more reasonable, likely taking register selection directly off the instruction encoding. Anyway, that's a little bit about me. Another thing is I have a difficult time talking about me from my perspective. I would much rather answer questions. So if you've got any questions about my background or what I bring to the table or what in the heck I'm doing trying to make something different than Ben or James, go ahead and leave it in the comments. Okay, you will have seen me actually pull the unused bits out of pins 4, 5, and 6 on this buffer and replace them with the inverted clock signal going in, so the inverted clock signal was buffered. I had missed that before and figured I'd better clean that up. You've also seen me introduce some gray wires, which I want to use for driving LEDs. So that is a new color on the boards. White again is following clock and inverted clock signals. And the green is for just connections within the board. I may change the inverted clock signal to be a different color, depending on A, if I have enough colors, and B, what everything else sorts out to be. But I have a feeling by the time I get to that kind of a point in time, I may be working on a PCB associated with that. The next thing is to take this and wire that in as well, so that when it comes on, rather than a blue LED, I'm using this red LED here at the end. So let me work on that. Moving over the Power Supervisor, you'll notice that the red LED was very dim. I had a 20,000 ohm resistor on that and ended up changing that to be a 2,000 ohm resistor for this LED. Different LEDs, different diodes, as a matter of fact, have different voltage forward and different current forward in order to get the LED to light. And with this particular LED, it needed a little bit more current in order to be brightly lit. So I just reduced the resistor in order to give me a brighter LED. That was a very simple change. Okay, that's it for this board. Notice that when we have a reset condition, the red light now lights up. Should be relatively easy to identify that that's actually happening. I have my manual clock. I have my automated clock. And I'm going to call this board finished. Up next, I want to have a conversation about decoupling capacitors. I'm not sure that I have the same conventional wisdom that everybody else does on this, so I need to get my head around this a little bit, and explaining what my thought process is may reveal something even to myself. I do still have a couple of things related to the clock. There are the variable resistor. I want to go do an upgrade to that, so I'm not twisting the little blue one I have right out of the board. And then I want to get into KiCad and do a clock circuit design. Now, I've called it KiCad in the past, and I've been corrected that it's supposed to be KiCad, so I have to learn how to say that differently. I don't want to do the clock stuff right away. I will likely end up getting into the register breadboard layout and do that ahead of any of the other clock module related things. See you soon.